Hi guys, today's lesson is 3.8 on rational functions. So rational functions are something that we started studying in 20-1 or 30-2, and we're going to take a look at some graphs today and the characteristics that they have. So things like domain, range, intercepts, and asymptotes. So the first thing I want you to do is sketch y equals x, or f of x equals x, and then I'll show you how to do the reciprocal. So the equation y equals x should be pretty simple to graph. It's just where all of the xy coordinates have the same number. So like 0, 0, 1, 1, 2, 2. So that would be this diagonal line that cuts through the Cartesian plane through all those points. Now the reciprocal is what happens when we take this original function y equals x and we make it y equals 1 over x. So these are going to have fractions that we need to look at. When we studied these in grade 11 or in 30-2, we always stated something called an NPV. An NPV was where the denominator would become 0. So in this case, we have x in the denominator. One of the golden rules in mathematics is that you can never divide by 0. So we would state that x cannot equal 0. That was an NPV, a non-permissible value. What that does when you're trying to draw the reciprocal is it creates something we call an asymptote. So it creates at the line x equals 0, a dotted line that we never touch. So this is the line x equals 0 in blue. I'm going to write it at the bottom. And this is what we call our vertical asymptote. Now for this one, there's also a horizontal asymptote that exists at y equals 0, and I'll show you in a future question how to find that from the equation. And then we're ready to draw a reciprocal. Before we get going too far, let's just state everything we know about f of x so far. So the green line, y equals x. The domain of a linear equation like that is XER. It goes on forever and ever in both x directions. It also goes up and down forever, so YER for the range. The x and y intercepts are both the same. If you look at that, it crosses on the origin, so 0, 0. Invariant points we're going to state in a minute. And then the asymptotes we said were x equals 0 and y equals 0. Or in this case, the x-axis and the y-axis. Let's just move those over. I'm going to put those under the reciprocal equation because technically this linear one doesn't have any asymptotes yet. Now the way that we're doing reciprocals is we're going 1 over the original function. And that's something that we're going to do for all y values. Remember that f of x is a y value. So to determine my reciprocal graph, I'm going to take some y values from my y equals x graph, and I'm just going to flip them and make them a fraction. The first thing I'm going to do, though, is I'm going to put my invariant points on here. Invariant points are numbers that if I flip them in a fraction, I get the same number back, like the number 1. The number 1 is secretly 1 over 1, and if I flip that fraction, I get 1 over 1. It's the same number. So those are what invariant points are called. They occur at points where the y value is 1 and also negative 1. Or pardon me, they occur where the x value, let's write that down, is 1 or negative 1. Now we're going to take some numbers that we can flip pretty easily. I'm going to go up here to a value of 2 on the y-axis, and I'm going over to where I hit my graph. If I take the number 2 over 1 and I flip it, that becomes 1/2. So this y value was at 2, and now it's going to be at 1/2, which is right there. I'm going to take a value of 1/2 on my original graph, and I'm going to flip that. If I flip 1 over 2, it becomes 2 over 1. That would happen for all the points along the line. Things like 3, 4, 5 would be a third, a fourth, a fifth, and so on. Things like a third would jump to 3, a fourth would jump to 4. That's how we get this shape for reciprocal functions. They get really close to the asymptote but never touch, curve through the invariant point, and then get really close to the next asymptote. This happens in whatever quadrants that you have the original graph. So the original graph was in quadrant 1, so I have the red function that I drew there, but also in quadrant 3, which would give me a very similar shape if I started flipping y values. This red graph is the function 1 over x. If you try graphing that in your graphing calculator, you will see something similar, but the graphing calculators don't put the asymptotes in for you. All right, so what do we notice about the red graph? Does it ever touch the y-axis? Well, no, the y-axis is an asymptote, and by definition of asymptotes, it cannot touch. So there are no y-intercepts, and for the same reasoning, no x-intercepts. The range looks to me like the graph is everywhere except for on that asymptote. It goes up forever, down forever, but it never actually touches y equals 0. So the way I'm going to write this is y cannot equal 0, but y is every other real number. Same idea for the domain. This red graph is pointing to negative infinity and positive infinity, but it never touches the line x equals 0, aka the y-axis. Now, below this, we have vertical and horizontal asymptote shortcuts. The vertical asymptote is what makes the denominator equal to 0. This is what we've all worked with before as an NPV. So you find your non-permissible values of the denominator, and those become your vertical asymptotes. Horizontal asymptotes are a little bit different. You divide the coefficients of the highest degree terms. In this case, the highest degree term we have is x to the 1, degree 1. On the top, there isn't an x to the 1. So I would have to write this as 0x plus 1 over x. And remember, that has a secret 1 in front of it. I just put a 0 in the place of what wasn't actually there. Now, what they're saying when they say divide the coefficients of the highest degree term is if x is our highest degree term, divide those coefficients or those numbers in front. 0 divided by 1 is 0, so your horizontal asymptote is going to be y equals 0. This will make more sense when we have questions that have actual numbers, but it's a nice shortcut. Let's try this function. 4x minus 5 over x minus 2. This is a reciprocal function because it is a fraction. So for this function, we want to try sketching it, and we also want to state all of the characteristics. First thing I want you to tell me is, what are the NPVs for this rational equation? What makes the denominator 0? If you recall from your last course, I take my denominator, x minus 2, I set it equal to 0, and I do algebra to solve for x. My NPV for this one is x cannot equal positive 2. The shortcut that we taught you in your last course was if it has a plain old x in it, see how it was minus 2 to begin with? That makes our NPV the opposite sign, plus 2. Now, once you have your NPV, you can immediately go ahead and put on your vertical asymptote. Your vertical asymptote always has to be written as an equation. It's the line x equals 2. Instead of writing does not equal like I would with an NPV, I just make it an equal sign and I draw a vertical line where x is equal to 2. I make it dotted so that I can show it's an asymptote, and I put the equation at the bottom or the top, doesn't matter. Horizontal asymptote is going to be when you divide the coefficients on the biggest exponent x has. The biggest x's I see here are x to the power of 1. I'm going to divide the numbers in front. Secret 1, 4 divided by 1 equals 4. So the horizontal asymptote is the line y equals 4. I'm going to go to where y equals 4 on the graph, and I'm going to draw another asymptote, this time horizontal, and put the equation at the end. Now, xy intercepts we've studied before. What I tried to get you to do is to think about xy intercepts as something equaling 0. So if I'm looking for an x-intercept, what value is 0? Well, y is always 0. So in the equation, I'm going to make y 0, and I'm going to solve for x. Now let's talk about the algebra that you would use here to solve for x. You would first want to get rid of the fraction by multiplying both sides by x minus 2. If you think about it, that's going to cancel x minus 2 on the right-hand side, and the left-hand side is 0 times something. 0 times anything is 0. So this is actually a shortcut that you can take. The 0 is going to be equal to the numerator. This step happens every single time. So you can jump to this step where 0 equals the numerator because you know the denominator is going to multiply by 0 and therefore be 0. Then I'm going to do my basic algebra steps to get an x-intercept at 5/4, about 1.25. Go ahead and put that point on your picture. Crosses the x-axis at about 1.25. And let's do the same process for the y-intercept. Y-intercepts are going to have an x value of 0. So in my original equation, wherever I had an x, I'm going to write a 0 instead. Think about what this does. This means that any term that had an x in it disappears. All you have to do for your y-intercept is you have to divide the constants, the numbers in there that don't have x's. So -5 and -2, be careful with your signs, gives you a y-intercept at 5/2. Let's write down what these shortcuts were for your notes. We divided the constants to get a y-intercept, and we put 0 equal to the numerator, and then we did algebra to find the x-intercept. I'm going to go ahead and put my y-intercept on my picture now, about 2.5. And I should be able to kind of sketch in what this would look like now. I can kind of see the shape forming down here. And then I'd have a similar shape forming up here. This is something that you can enter into your calculator. I'm going to do that now. And you can make sure that it looks similar to what you've sketched. You need to make sure when you're entering it in your calculator that you put the top in brackets and the bottom in brackets before you hit graph. It's important to take a look at what the calculator looks like because it doesn't show the asymptotes. It just shows what I've sketched in blue. Let's fill in the rest of this. it looks to me like this graph goes to the left forever and the right forever. So the domain is all real numbers except where we've drawn an asymptote. We've drawn an asymptote where x is equal to 2. Asymptotes are spots on the graph where the graph cannot live because it would mean division by 0. So we have to say that the domain is x cannot be 2, but x can be every other real number. By the same logic, y cannot be the asymptote 4, but y can be any other real number because there's arrowheads pointing up and down. We found the x-intercept algebraically. It ended up being 5/4, 0, and the y-intercept was 5/2. Let's try another one. First thing I'd like you to do in this question is tell me the vertical asymptote and the horizontal asymptote. Try pausing the video, looking back, and seeing if you can find those on your own. My vertical asymptote is my NPV. In this question, x cannot equal 4, switching the sign. So that's going to be x equals 4 for my vertical asymptote, which lives on the graph right here. My horizontal asymptote is going to be the coefficients of the largest exponent x has divided. So 2 divided by 1 is 2. There is a horizontal asymptote at y equals 2. Now I'm going to try and find my xy intercepts so I can get an idea of where we're crossing those axes. I'm going to do it algebraically by setting x-intercept y as 0. So 0 is equal to 2x plus 2 over x minus 4. But I'm going to apply the shortcut that I taught you on the last question. The denominator is going to multiply by 0 anyways and disappear. So I'm not going to write that step. I'm going to proceed with algebra and get an x-intercept at -1. Go to your graph and put a point at an x value of -1 on the axis. My y-intercept is where all of my x's turn into zeros, which looks like this. But the x terms always cancel. So you really can just divide the constants, the terms without x's, simplify them, and that gives you your y-intercept at -1/2. We should be ready now to state the rest of our characteristics and give ourselves a sketch. According to my asymptote, x cannot equal 4, that's my NPV, and my vertical asymptote, but x is every other real number. Similarly, y cannot equal the horizontal asymptote of 2, but y is an element of the reals. The x-intercept I calculated at -1, and the y-intercept was at -1/2. Putting all of this information together and looking on my calculator, I see getting close to asymptotes down in that corner, going through my intercepts, and a similar thing happening up in this corner. All right, next example. We have 3 over x squared minus 10x plus 25. This looks different than anything we've done so far. What we've done so far has come from linear equations, and the biggest degree you've seen is a degree 1 on your x's. This has a degree 2. It comes from the reciprocal of a quadratic. So this is going to look slightly different. When we had something like this last year or last semester, to find the NPVs, we would factor the bottom. So you need to know your methods of factoring, or you need to be able to use a quadratic formula here. When I think about this one, I want to find two numbers that multiply to 25. Whoops. Let's go back there. Sorry about that. Okay, I'm trying to draw my diamond here to show that I'm multiplying to 25 and adding to negative 10. So you think through all the ways that you can multiply to get 25, and which of those ways also adds to negative 10? Negative 5 times negative 5 is positive 25, and negative 5 plus negative 5 is negative 10. So now that it's factored, I can see that my NPVs are x cannot equal 5. They're both the same bracket, so they only give one NPV at 5. Now we have to put in some extra terms on top so we can match the biggest degree on the bottom. The top just has a 3, but the bottom has an x squared. So the top here would be the same as writing 0x squared plus 0x plus 3. Now that I have all the terms written, I can go ahead and divide the coefficients on the biggest degree, x squared, to get my horizontal asymptote. So 0 divided by 1 is 0, and that's where my horizontal asymptote is for this one. Go ahead and pause the video and see if you can fill in the equations for the asymptotes and start on the xy intercepts. All right, I'm going to just fix this, put my equation on my horizontal asymptote, and fill in the chart. And now I'm going to proceed to find my x-intercept algebraically. So remember, your x-intercept is where y is equal to 0. We know that we would start by multiplying the denominator by this 0. 0 times anything is 0. Take a look at what you've just written down and what you're actually saying here. You're saying that 0 equals 3. And anybody that looks at that would say, 0 does not equal 3. If I have $0, it's very different than $3. Those are not the same thing. So when you're doing algebra to find something like an x-intercept and you get a mathematical lie, this cannot happen. 0 does not equal 3. That's not true. That means that whatever you were trying to find, which in this case was an x-intercept, that means that there isn't an x-intercept. So that helps us to sketch this. We know that when we sketch this, we are never going to touch the x-axis because we can't find one algebraically. Let's see what happens now for the y-intercept. Y-intercepts are where x is 0, which is 3 over 25. So y is going to be a y-intercept at 3 over 25. That's pretty small decimal, close to 0. And we're never touching the x-axis. So that means that we must be above this horizontal asymptote because the x-axis is below it. So, or the x-axis is on it. So what's happening is if we've got a y-intercept that's at 0 point something, we've got to have this part above the x-axis there. Now, if you put this in your calculator, you'll see that this makes a slightly different shape. And I'm going to show you why in a second. This makes a shape where actually both of the reciprocal parts of the function are side by side. They're both above the horizontal asymptote here. That comes from the fact that the original function, x squared minus 10x plus 25, was this kind of shape. Remember quadratics? It gave you a parabola shape. So if those tails of the parabola are both pointing up like that, and you take the reciprocal of all the numbers that lie on these tails, then you get these red parts matching up with where the black ones are. You're not going to have an original function that's up here and then you have something drawn down here. That's not possible. That's not how reciprocals work. Wherever the original was, that's where you're going to have the reciprocal function. Okay, so this one looks a little bit different. But here we go with the domain and range. They're still the same. X cannot equal 5 because it's an NPV and the vertical asymptote, but it's all other real numbers. Y cannot equal 0, but YER. An x-intercept, mathematical lie, so there is none. And y-intercept was 3 over 25. Now this question I believe I added in addition to the notes that are posted, so you might have to draw this set of notes on a separate piece of paper. This one is going to be 2x squared minus 5x minus 3 over x squared minus 1. I'm going to start by factoring the denominator. This is a difference of squares that factors to be plus 1 minus 1. So our NPVs are plus and minus 1, which in this unit corresponds to vertical asymptotes at -1 and +1. Something strange that we haven't seen yet, but I'll show you exactly why it's kind of weird in a minute. We're now going to take the biggest degree we see, which is x squared, and divide the coefficients to get our horizontal asymptote. 2 divided by 1 is 2, so our horizontal asymptote is at y equals 2. Pause the video and try and state domain and range right now for that. So domain would be x cannot equal positive or -1, but it's all other real numbers. Y cannot equal 2, but it's all other real numbers for the range. The asymptotes, vertically, we have 2. Horizontally, we have 1. X and Y intercepts are next. The shortcut for finding an x-intercept is saying y is 0 equal to the numerator, which was 2x squared minus 5x minus 3. Now this is something that we should be able to factor or use the quadratic formula if we want. I'm going to factor it. It's easier. Multiplies to 2 times -3, which is -6, adds to -5. Those two numbers are going to be -6 times 1, -6 plus 1. I'm going to do factoring by decomposition. So the middle, -5x, is becoming my magic numbers with x. You can see the substitution there. Then I'm going to cut this in half, and I'm going to take a GCF out of the left-hand side and a GCF out of the right-hand side. Since my first term is negative, I'm going to take a negative out of this side. Whoops, this should not have been negative, pardon me. So I'm not going to take a negative out, and I get x minus 3. There we go. Now, this method of factoring has a built-in double check that these two brackets should match. When they do, you write your final answer as one of those brackets and the things that you GCF'd out. Now, from quadratics, we know that these create x-intercepts at, switch the sign, x equals 3. And this one you might want to do by hand. Set it equal to 0, perform your algebraic steps, and you get another x-intercept at negative 1/2. So 3 and negative 1/2 are my x-intercepts. I can go ahead and put them on my x-axis now. And do the same thing for the y-intercept. Y-intercept is where all of my x terms disappear. So 2 times 0 squared minus 5 times 0 would all just be 0. And I'm going to take my constant on top and bottom, and I'm going to divide those. So my y-intercept is negative 3 divided by negative 1, which is 3. So this one is quite tricky. I want you to try and put this into your calculator right now, because this one does something that we've never seen before. We certainly have never seen this in, we've never seen this in grade 11 or in 30-2, because this does something weird on the inside. So on the inside here, what it's actually doing, if I sketch this really carefully, is it's actually crossing the horizontal asymptote in the middle there. This is something that you don't need to know in too much detail. You just have to pay attention to this note I have right here, this starred note. It is possible to cross a horizontal asymptote on equation. Vertical asymptotes, however, are never going to be crossed. Okay, we just don't cross them. All right, so what we end up having here is we end up with that kind of shape in there. And we end up with this kind of shape up here. I was just trying to figure out my error. I've got my x-intercept, my negative 1. I've just got it slightly in the wrong spot here. Right there. Sorry about that. So now we've got kind of this funky looking graph that has the two parts of a reciprocal that we're used to seeing, but it has that middle wonky bit that does cross the horizontal asymptote. Don't worry about that. Just follow it from your graphing calculator. It is something that's allowed to happen for horizontal asymptotes, but just doesn't happen for the vertical asymptotes. Other possible graphs that I haven't given you examples of here, there's two I want us to sketch. I'm going to draw the original. So if we had a parabola that, let's say, looked like this. So this might be something like x squared minus 6x minus 9 or something like that. It's got a y-intercept below the x-axis and two x-intercepts. If you think about this, it's going to end up having vertical asymptotes at the x-intercepts, because that's where you would divide by 0, horizontal asymptote at the x-axis, and then all of the points on this graph, like let's say this point down here at -9, would flip up to be a fraction, -1/9. What happens is you end up getting this bottom part that looks kind of like an N. In the tail parts, you end up getting that same reciprocal look that we've seen all day. So what I've sketched here in blue is another possibility of a reciprocal graph. They can have all sorts of different looks to them, so there's not just one size fits all. Think on this side about a parabola that might be floating up in this quadrant here. If you take all of the y values on this graph, like let's say this is at 5 and this is at 10, 5 would be flipped to be 1/5, 10 would be flipped to be 1/10. This whole graph would get really close to the asymptote, kind of bump up a little bit in the middle, and then keep going. This is one of the most bizarre looking rational graphs that we have, but this too is a rational graph. There's no vertical asymptotes because it never crosses the x-axis, but there is a horizontal asymptote on the x-axis here. The next slide I added in last year, talking about the transformations that would take you from 1/x to 5/x plus 2 minus 6. We aren't going to worry about that during our COVID emergency learning that we're doing, so you can skip by that. And for this lesson, page 442, number 1, 3, 4, 5, and 8. Let me know by email if you have any questions.